the beginning of 4.3, we learned the first derivative test for local extrema. We said if a function f has a relative maximum anytime its first derivative changes from positive to negative, because that meant f changed from going uphill to coming downhill. And there was a second part for where f has a local minimum. So now we want to learn the second derivative test. It's not the second of two tests, but a test about using the second derivative. So we said that the second derivative tells us about concavity. So imagine a function that is concave down. Looks like an umbrella or some part of an umbrella. If a function is concave down and changes direction, changes from increasing to decreasing or decreasing to increasing, then whatever local extreme value it had must have been a maximum. So if f prime of c is 0 and f double prime of c is negative, so that means if there's a critical point on f and we find out that the second derivative is 0, meaning their function originally was concave down, then f of x has a local maximum at x equals c. If, on the other hand, f prime of c is 0, so there's a critical point, and f double prime is positive, which means the function must have been concave up. Here's concave up. I keep trying to do that. I'll draw my picture later. Concave up. If I have a local extreme value, it must be a local minimum. So that's what goes here. If f prime of c is 0 and f double prime of c is... that can't both be negative. All right. Very serious typo, guys. Those can't both be less than 0. The first one was less than 0, so this one should be if f double prime of c is greater than 0. So if f double prime of c is positive, that means my function is concave up. I was saying the right words, but it's printed wrong on your paper. Then f has a local minimum. Local minimum value at x equals c. Remember, another name for local minimum is relative minimum. So watch why we would need to know the second derivative test. You might think that, oh, okay, I can probably just get away with using the first derivative test all the time. And you're going to use the first derivative test a lot. I would bet you use it 5 or 6 times, maybe even more on the AP test. But there are some cases where we can't apply the first derivative test, but the second derivative test is available to us. So check out this release problem. I have this curve, which cannot be, I can't isolate the y. So if I want to find dy dx, I'm going to need to use implicit differentiation. So I'm going to leave step A for you. They've actually given you dy dx and asked you to show that that's the right dy dx. So you're going to use implicit differentiation. Don't forget the product rule. Don't forget the product rule. Second step, part B, show that there's a point P with x-coordinate 3 at which the line tangent to P is horizontal. I'm going to leave that one up to you. Now we're going to find the second derivative of y with respect to x at that same point P. And does the curve have a local maximum, a local minimum, or neither at point P? I guess I can't leave that part up to you. We'll have to do B together. All right. So here we go. I want me out of the way. All right. So for there to be a point P at which the tangent to that curve at P is horizontal, then I must know that at some point dy dx equals 0. Horizontal tangent. Tangent has 0 slope, slope is 0, derivative is 0. So dy dx has to equal 0. Notice my dy dx is a fraction, and a fraction is equal to 0 when its numerator is equal to 0. So I know that 0 has to equal 3y minus 2x. And check this out. They've told me that my x-coordinate has to be 3. So 0 equals 3y minus 6. tells me y is 2. I'm going to confirm that 3 comma 2 is on the original curve by checking in my original curve. So I'm going to say 3 squared plus 4 times 2 squared has to equal 7 plus 3 times 2 times 3. So 9 plus 16 has to equal 3 is. So this is me checking that I have that the ordered pair 3 comma 2 is in fact an ordered pair on this function. So I'm looking up here, this equation, and I'm using 3 for x and 2 for y, and I'm just confirming I make a true statement. So on the left-hand side, 9 plus 16 equals, on the right-hand side, 7 plus 3 times 2 is 6 times 3 is 18. And that is a true statement. So 3 comma 2 is on this curve, and at that ordered pair, the slope is in fact 0. So my answer to question 3, well, I did 2 things. I set dy dx equal to 0 and x equal to 3, and I solved to get y equals 2. And then I confirmed that 3 comma 2 is in fact a point on the curve. So 3 comma 2. It's not that that's the answer, but that's the thing I'm going to need for part 3, part C. So for part C, I'm going to find the second derivative at 3 comma 2, and then I'm going to use that second derivative evaluated at 3 comma 2 to find out if my original curve has a minimum, a maximum, a local minimum, a local maximum, or neither at point P. So here's what I'm going to do. I need my second derivative, so I'm going to scoot some of this stuff out of the way. All right, so we're going to try something. This whiteboard. All right. I don't know if this is going to work. We're going to try it. But let's face it, me writing in that pen isn't really working for anybody. All right. There's my dy dx. I'm going to find my d squared y dx squared. I'm going to use the quotient rule. I'm going to not hold the iPad while I do that. Hold on. All right, let's see if that's better than me trying to write with a electronic pen. So I've used the quotient rule. That's low d high minus high d low all over low squared. My next step is going to be to evaluate that second derivative at the place where x is 3 and y is 2. Just notice that before I do that, I'm going to have those, I see 2 places in my second derivative where I have the expression y prime. Y prime is another name for dy dx. And if I'm going to evaluate everything else at 3 comma 2, I'm going to need to evaluate y prime also at 3 comma 2. So I'm just going to make a little note up here. Let's see if we can do this at the same time. That means dy dx evaluated at 3 comma 2 is interesting to me. I've actually already simplified this, well, in a sense. So that's going to be 3 times 2 minus 2 times 3. Oh, right. So remember that we wanted a horizontal tangent, minus 3x. And that was because this value was going to, that numerator was going to be 0. This is going to be 8 times 2 minus 3 times 3. It doesn't really matter because that numerator is 0. So dy dx at 3 comma 2 is 0. So now when I'm going to evaluate my d squared y dx squared at 3 comma 2, anytime I see y prime, I'm going to be able to replace it with 0. I'm going to do that next. This is my second derivative with all the x's replaced with 3 and all the y's replaced with 2, and my y primes replaced with 0. So I'm going to simplify this as much as just notice I could leave it like this if the question was what is d squared y dx squared at 3 comma 2. But I'm going to I have that next question to answer, which is, does the original curve have a relative minimum, relative maximum, or neither at 3 comma 2? So I'm going to be using the second derivative test, which says if I find a critical point, which means the first derivative is 0, and I can figure out the sign of the second derivative, I'll be able to tell if that critical point was the top of a hill or the bottom of a valley, and that'll tell me if it was a relative minimum or relative maximum. So I'm going to need to simplify as much of this as necessary to figure out if the result is positive or negative. Hold on. All right, so I simplified that a little bit. I know that 3 minus 2 minus 2 minus 3, that's going to equal 0. So that whole second half of my numerator after the subtraction sign is going to simplify to 0. I'm going to have a positive 7 times a negative 2 all over 7 squared, which is negative. So I wrote less than 0. Don't simplify any more than you have to, at least not on the free response section. So we have found the second derivative at 3, 2. It's negative 14 over 7 squared. And I figured out that that result is negative. So that tells me this is the second derivative. If my second derivative is negative, my function must have been concave down at 3, 2. And I had a critical point, which was the first derivative was equal to 0. So I know that my direction has to change, so I'm going to change either from increasing to decreasing or decreasing to increasing. If I know there's a critical point and my second derivative is negative, then that must have been the top of a hill, which means my original curve must have had a relative maximum. So I'll write that up. All right, so here's what I would say. I would say since dy dx, oops, that should have been a straight line, evaluated at 3, 2 equals 0, and d squared y dx squared evaluated at 3, 2 is, oops, not positive, it was negative. By the second derivative test, the curve has a local, so negative second derivative means concave down. So if I had an extreme value there, that was the top of a hill, that was a local maximum at 3, 2. Final answer.